Okay, we are going to look at the vascular system and just review a few key concepts. So remember, the vascular system is a continuous flow system. It goes from arteries, arterial, to capillaries, to venules, to veins, and then back to the heart. And the capillaries is really where all of the action takes place because and it's as a result of its structure. So there are multiple layers in the vessels, but capillaries only have the internalmost layer, so the tunica intima. Because capillaries have a single cell lining the vessel, this is where the exchange takes place: exchange of fluid, exchange of nutrients, exchange of oxygen, and exchange of waste. And so any alteration of the pressures and the cellular structure can result in a net inflow or outflow of fluid. And so we're going to talk a little bit about edema and effusions, but first you have to know what pressures regulate fluid exchange. Okay, hydrostatic pressure. Hydrostatic pressure, anytime you hear hydrostatic pressure, I want you to think blood pressure. For our purposes, it is exactly the same thing. So blood pressure is hydrostatic pressure, okay? Blood pressure or hydrostatic pressure pushes fluid out, okay? So especially at the very beginning of the capillaries, where the pressure is higher than at the end, you're going to have a net outflow of fluid. And hopefully there is going to be something else that helps bring some of that fluid back in. And the pressure that we're going to talk about that sucks in the pressure or sucks in the fluid back into the capillary is osmotic pressure. And so hydrostatic pressure or blood pressure is out, flowing out, and then osmotic pressure sucks the fluid back in. So what determines osmotic pressure? This is really the large molecules like albumin that are floating in the fluid. So this is kind of, you can think of it almost like osmosis. Because we just pushed a lot of fluid out with the blood pressure at the very beginning of the capillary, relative to that beginning, towards the end of the capillary, it's relatively concentrated in terms of the fluid and solute ratio, right? And so because it's relatively concentrated, that forms a gradient by which water can come back into the capillary. And so that is the osmotic pressure. And again, albumin is our main determinant of osmotic pressure. What is albumin? It's a big protein, basically. And so, and albumin is very sensitive to your nutritional status. And so in a case where someone might be malnourished, they might not have the building blocks to build albumin and these big macromolecules that are floating in the blood. So they might not have as much to, make that concentration gradient to suck in all of that water. And so in that case, water is going to stay out because there was a, even normal hydrostatic pressure, but not a normal osmotic pressure to suck it back in. So the other thing that really regulates this, and I will go back to the vessel structure. So the other thing is the integrity of the endothelial cells. So remember, capillaries are lined by single cells, right? It's only that tunica intima. And so any disruption of that lining, you can really have some, net outflow of fluid. And so the factors that mediate exchange of nutrients between blood and extracellular space: hydrostatic pressure, which is your blood pressure; osmotic pressure, which is basically albumin or the proteins in the blood; and then the integrity of endothelial cells. And that just means that the structure is intact. And if it's not, then of course you have a net outflow of fluid. So let's do a couple of examples. So case 1, edema develops after you infuse IV fluid into a patient. So remember like chemistry, I think, where you have a volume and a pressure relationship, right? And so what happens when you put more volume into a closed system? So what are we working on? What factor are we working on? Are we working on hydrostatic pressure? Are we working on osmotic pressure or integrity of the endothelial cells? If edema develops after you infuse IV fluids into a patient, what pressure are we dealing with? So an increase in hydrostatic pressure, right? Because we just put a whole lot more volume into the system, which increased the pressure. Case 2, a teenager with anorexia develops swelling of her legs. What factor is causing edema in this scenario? So a decrease in osmotic pressure. Remember, osmotic pressure is regulated by albumin, which is a protein, which is very sensitive to nutritional status. So we could cause edema by increasing the hydrostatic pressure, decreasing the osmotic pressure, or there's one other mechanism. So a person with injury develops swelling of the ankle. What mechanism resulted in the edema in this case? So an alteration of endothelial cell integrity. So anytime you get a question about edema or effusion, you really only have to know the direction of 3 factors, right? Was there a change in the hydrostatic pressure? Was there a change in the osmotic pressure? Or was there an alteration of the endothelial cell integrity? And that's it. So there are so many causes of edema or effusion, but again, the main pathophysiology that explains this is the hydrostatic pressure, osmotic pressure, and the other ones that are listed on this table, the mechanisms. Inflammation really has to do with that endothelial cell integrity. Why? Remember what histamine does. Remember, your mast cells release histamine at the very beginning of that inflammatory cascade. And what happens? It makes the endothelial cells contract. And so then there's room in between each cell for the fluid or the white blood cells or whatever to go out. And so that's disrupting the endothelial cell integrity. Lymphatic obstruction is something we're not really going to talk about a whole lot, but basically it's going to increase your hydrostatic pressure. And sodium retention, that also works by increasing the hydrostatic pressure because water always follows sodium. And so if you have an excess of sodium, then you are going to increase your fluid retention, and that's going to lead to more volume in the system, which equals more pressure. There's other ways that it works too, but we're not there yet. So the other picture, the other chart on this slide goes from the beginning to the end of edema, right? So heart failure, what does heart failure mean? Well, in general, your heart is just a pump and you want it to go forward, right? You want the blood to go forward in the system. But if your heart is failing, then things start backing up and things can't move as forward as easily as they previously did. And so when you have a backup, then you have increased hydrostatic pressure, which leads to edema. And then there's another way that it works too, which we'll talk about in a minute. And that's really through the renin-angiotensin system. Because fluid is backing up, because blood is backing up in heart failure, it can't move forward. So the organs that usually get that blood flow on the, forward end of the heart aren't getting as much blood flow. And so they're going to implement different mechanisms to adapt to this and try to conserve water by conserving fluid, by increasing volume, by increasing pressure. And then the other pathway on the right shows how malnutrition works. And remember, that really affects your ability to create these big macromolecules, the albumin. And so that's going to decrease your osmotic pressure. And then that creates edema.